Good day, esteemed researchers and curious minds tuning in from around the globe. We're diving into the fascinating world of video question answering with our study, STAR, a benchmark for situated reasoning in real-world videos. This research tackles the challenge of enhancing complex task, understanding, and improving reasoning capabilities in models. We'll explore the limitations of existing models, introduce our innovative dynamics model, and discuss intriguing insights from our evaluation. So buckle up for a journey into the future of video question answering. The motivation behind this paper is to enhance the performance of video question answering tasks. We've identified that existing models, while effective in certain areas, struggle with complex tasks and reasoning. This is a gap we aim to address. We've examined various models, including Q-type models, blind models, vision language models, and video question answering models. Each of these models has its strengths and weaknesses. For instance, Q-type models follow a random probability distribution, while vision language models can grasp coarse-grained visual and language representations. However, they fall short in video question answering tasks. Video question answering models show promise, with an average accuracy increase of about 5.03%. The best average accuracy is achieved by the Clip-BERT model, which reaches 36.79%. Despite these improvements, there's still a significant room for further exploration, especially in complex tasks and reasoning. In the next part of our research, we propose a transition model to process and predict situations, aiming to distill structured cues from dynamic real-world situations for further reasoning. This is a step towards addressing the limitations of existing models and improving video question answering tasks. Existing approaches have shown proficiency in representation, but often falter when it comes to video question answering tasks. They struggle with complex tasks and reasoning, highlighting a need for models that can handle these challenges. To address this, we propose a dynamics model. This model is designed to predict action states or relationships by learning the relations among input data. It's a robust system that includes a graph sequence decoder, a language parser, and a program executor. The graph sequence decoder is set up with 3 self-supervision tasks: action type prediction, human-object relationship type prediction, and masked token modeling. This helps enhance the representation robustness by reconstructing their embedding vectors. The language parser parses each question into a functional program, using an attention-based sec2-sec model. This allows us to parse the input questions into corresponding programs, making the process more efficient. Finally, the program executor answers questions by executing programs on discrete hypergraphs. It conducts symbolic reasoning for the answering and plays the role of the reasoning engine. Together, these components form a comprehensive model that can handle complex tasks and reasoning, addressing the problems faced by existing approaches. Our primary aim is to enhance the performance of video question answering tasks. We strive to improve the understanding and reasoning capabilities of models, which is a significant challenge as current models show diverse performances, and the average level overall baselines are still not good enough. To address this, we propose the nitrogen monosulfide SR architecture, as shown in the figure. This architecture is designed to distill structured cues from dynamic real-world situations for further reasoning. It processes and predicts the present and future situations in the form of hypergraphs, thereby improving the model's ability to handle complex tasks. This innovative approach is our motivation to push the boundaries of video question answering tasks. In our exploration of existing models, we found that Q-type models, blind models, vision language models, and video QA models each have their unique strengths. However, they all share a common struggle with complex tasks and reasoning. Basic models, for instance, show no option biases and follow a random probability distribution. Yet, they reveal the limitations of simple vision language models in video question answering tasks. To address these challenges, we propose a novel dynamics model. This model is designed to predict action states or relationships by learning the relations among input data types in situation videos. It employs a multi-layered architecture of stacked transformers with downstream task predictors. This innovative approach allows us to dynamically predict and understand complex situations, opening new avenues for video question answering tasks. Our research proposes a novel dynamics model that predicts action states or relationships by learning the relations among input data types in situation videos. The architecture of this model is composed of multiple layers of stacked transformers with downstream task predictors. Now, let's delve into the specifics of the dynamics model. It employs transformer blocks to calculate self-attention scores for the input token sequence. These attention scores illustrate the potential relationship connections within situation graphs. An important aspect of this model is the aggregated effect, which is stored in the current state and then applied to the prediction for missing information. This dynamic attention modeling handles all possible relations as implicit connections, making it robust even when relationships are unknown or visual clues are unreliable. In essence, this model is designed to dynamically predict and understand the complex relationships within situation videos, providing a robust and efficient solution for action prediction tasks. Our research introduces a graph sequence decoder, which incorporates 3 self-supervision tasks. These tasks include predicting action types, human-object relationship types, and masked token modeling. The latter is particularly interesting as it enhances the robustness of representation by reconstructing embedding vectors. We also developed a language parser that transforms each question into a functional program. This transformation is achieved using an attention-based Sec2-Sec model. The functional program is composed of nested operations, providing a structured approach to parsing. To ensure comprehensive parsing, we use 2 models to parse the questions and choices individually. This dual model approach allows for a more nuanced understanding of the input data. In essence, our research combines the power of graph sequence decoding and language parsing to create a dynamic and robust model for predicting action states and relationships. Our research introduces a program executor, a key component of our model. This executor is designed to answer questions by executing programs on discrete hypergraphs. It plays a crucial role in our system, acting as the reasoning engine in nitrogen monosulfide SR. The executor takes as inputs both the program and the predicted situation hypergraph. It then executes functional operations in a systematic and orderly manner. This approach allows us to handle complex reasoning tasks and provide accurate predictions. Diving into the technical results, we find some intriguing implications. Our findings clearly show that there is ample room for further exploration and improvement in video question answering tasks. This is a field ripe for innovation and advancement. The highest accuracy was achieved by the Clip-BERT model. This suggests that models which extract object interactions or better visual representations have a significant edge. They are able to perform better, indicating the importance of these factors in the model's performance. Moreover, we observed an increase in accuracy when transitioning from simple visual language models to video QA models. This indicates the potential of these models in improving performance. It's a promising sign that we're on the right track. And with further refinement, we can expect even better results. In summary, our technical results point towards a future where video question answering tasks are more accurate and efficient, driven by models that can effectively extract and utilize visual representations and object interactions. As we draw conclusions from our research, let's take a moment to revisit the key contributions of our work. We've introduced a novel dynamics model designed to enhance the performance of video question answering tasks. This model is built upon stacked transformers, which dynamically predict action states or relationships by learning the relations among the input data types in given situation videos. In addition, we've incorporated a graph sequence decoder, a language parser, and a program executor into our model. These components work together to improve our understanding of complex tasks and enhance our reasoning capabilities. On the right, you can see a visual comparison of model performances. This figure illustrates the effectiveness of our approach in comparison to other models. It's clear that our model offers significant improvements, particularly in handling complex tasks. In summary, our research presents a comprehensive approach to video question answering tasks, offering promising results and paving the way for future advancements in this field.